Hi everyone, I'm Jianglin, a graduate student from the School of Computer Science and Information Engineering at Hefei University of Technology. I'm glad to present the paper. The title of my paper is Random Target Track Prediction Based on Temporal Residual Self-Attention. Next, I will report the following aspects, including background, definition, method, and experiment results. First, let me introduce the background of the problem. Recently, the drone industry has been growing rapidly around the world. The following chart shows the global drone industry investment amount status from 2008 to 2019. Investment grew from $13 million in 2008 to $1.2 billion in 2019. Thus, growth has been applied to all aspects of life. For example, the application of drones for agricultural irrigation, fire prevention, and firefighting work, the maintenance of electric power facilities, logistics and distribution, and so on. However, as the use of drones become more and more widespread, it also brought some adverse effects, the most influential of which is the drop blank flight phenomenon. So what is drop blank flight? It refers the operation of drones in the no-fly zone without obtaining permission. It comes with some hazards like causing interference to air flights and endangering public safety. Next, we will talk about the problem. For track point data, we use longitude, latitude, height, angle, speed, and time to describe the track point data. The track point when at the ice moment can be expressed as follows. When a trajectory lasts for a period of time, we assume that the duration is n. Therefore, the trajectory for this period is represented as follows. To predict a certain attribute's value at moment I plus 1, we take as input the n track points before moment I plus 1 with a certain attribute's value at moment I, where the attribute's value at moment I is the same as the attribute's value at moment I plus 1. The methods for trajectory prediction are divided into two main categories, including ground target, air target. However, the ground target trajectory prediction and air target trajectory prediction have some differences, such as ground targets are slower and more stable in operation than drones, and the drone trajectories might change more significantly. Ground targets are relatively limited in their activity space, while drones have a huge flight space. For ground targets, their trajectory can be predicted based on the surrounding environment, social attributes. The ground targets are strictly influenced by stationary roads and points of interest on the horizontal plane, while air targets are not strictly controlled by stationary point of interest. Therefore, the trajectory prediction methods used for ground targets is not applicable for air targets. For air targets, there are three main types of methods, including track prediction based on mass motion model, trunk prediction based on good estimation, trunk prediction based on machine learning. But the existing trajectory prediction method for AI targets also have some problems, such as prediction methods based on mass motion model and hybrid estimation lack real-time and accuracy, and are too computationally complex. Among the trunk prediction using machine learning do not consider the temporal characteristic of the trunk points. The prediction method based on reference neural network still need to be improved when the time of trajectory is long. The traditional attention mechanism approach for trunk prediction doesn't represent global dependencies between trunk points well. Next, it is about the proposed method. To address the problem of predicting random trunk targets, we propose the trunk prediction model GISA. The model shows in following figure consists of 5 stages. Firstly, we use multi-height attention to calculate the interrelationships among all trunk points in a trajectory, so as to obtain a new representation of the trunk point. Next, we use the attentional features after the multi-height attention computation and the original trajectory information as the input of the future fusion layer, so as to obtain the fused representation. After that, we extract the features from the fused representation and through the fully collected layer obtain the new trunk feature vector. Then, we perform a multiple self-focused calculation on the future vectors and attribute values yi obtained in the previous stage, and calculated and nearly map the calculation result to obtain the final future vector of the trajectory. Finally, the future vector obtained in the previous stage are fed into the fully collected neural network layer. We use softmax as the activation function to obtain the to-be-predicted value yi plus 1. Next, I will introduce these 3 important modules in the model. The first module to introduce is self-attention based on temporal residue. First, we compare the traditional self-attention mechanism. Each input in the traditional self-attention method is divided into 3 representations: key, query, and value. So how to do the self-attention calculation? Firstly, to calculate the attention score based on Q and K, and then the weight value between vectors and are calculated based on the weighting factor V and the softmax function. Due to the traditional self-attention mechanism without considering the distribution of attention on the time axis. Therefore, our proposed self-attention mechanism, which considers the time differences between trunk points at different moments, introducing a time residue mechanism so that it will focus on the information of trunk points near the predicted moments. Next, we will introduce the computation of multi-head attention. The computation of multi-head attention is performed based on residues of k times of self-attention. In the calculation process, it is first necessary to perform a nearly mapping of Q, K, and V, that is, to make Q, K, and V multiply with different matrices. So the interrelationship between all trajectory points in a trajectory can be obtained by multi-head attention calculation. Finally, the attention feature fusion model is introduced. We use the result computed by multi-head attention and original trajectory information as two feature vectors, denoted by F1 and F2. Then fuse the two features vector by serial fusion. Finally, we will talk about the experimental results. Firstly, our dataset was obtained from the VeriFlight website, and we randomly select two flights data in this website. They are SW39 from San Francisco to Zurich, LH452 from Munich to Los Angeles. We divided each flight data into a train set and two test sets. We can see from the table that the number of points per flight, the number of flights. Second, some parameters in our algorithm are set as shown in the table below. As you can see, we set the length of our time series is set to 8. We set epoch to 300. We set the number of our server attention heads to 2, and so on. For the evaluation metrics, we choose two evaluation metrics: root mean square error and mean absolute error, which are commonly used for machine learning prediction tasks. To verify the prediction performance of the model, we consider both longitude and latitude. First, we validated the model prediction performance in longitude on two test sets. Then we validated the model prediction performance in latitude on two test sets. From the figure, we can see that the prediction results of our proposed model are quite close to the real data with small error. The proposed TRSA model is compared with three other models on RMSE and MAE, which are LSTM, GRU attention, and DSA-RNN. We can see from the table that our proposed TRSA model achieves the lowest RMSE with MAE in predicting both longitude and latitude. After analyzing the data in the table, it can be seen that the prediction performance index of our proposed model is much lower compared to the LSTM model without the inconclusion of attention mechanism, indicating that the attention mechanism can better focus on the dependencies between the track points in doing the track prediction problem, and thus make better and more accurate predictions. The table also illustrates that the model TSA achieves better prediction results compared with the GRU attention and DSA-RNN models that incorporate the attention mechanism. It shows that the traditional attention mechanism focuses only on the relationship between the track point information, which cannot represent the global dependence of the current prediction moment for all track points well. Thanks for listening. My report is over. Thank you.